Hello everyone. So welcome to IIT and Gate classes. So this is the continuation of gas dynamics video lectures. Today we will be talking about oblique shock waves. So in our previous sessions, we have seen energy equations and normal shock wave properties and isentropic relations and all. So today we will be talking about oblique shock waves. What do we mean by oblique shock wave? So that's what we are going to see today. Okay, so myself Akshay, so I'm from IIT. So whenever we see a flow which is seeing a corner, say like there is a angle at which a flow has to turn. So say like the flow may turn in this way, like concave corner, or flow can turn in this way. This is a convex corner, right? So nature has to establish such that flow will move smoothly so that we have to have some kind of a mechanism or some kind of feature so that allows flow to turn through an angle which is dictated by the geometry, right? So see here I have a corner which folds inward, that means like towards the flow. So here I have a corner which turns the flow away from the flow direction. So in both cases, how the flow has to happen? So when the geometry is such that which folds towards the flow, then we kind of see a flow is kind of compressed when it moves over here. Whereas when the flow has to turn through a geometry which moves away from the flow direction, then flow has to turn in this way. It means it has to expand. So in both the cases, a physics will change, right? So that's what we are going to see. So in today's session, what we are going to see is, we are going to see how these oblique shock waves are formed, or when flow faces a concave corner like this or compression corner like this, how the flow properties across the wave changes, and what in the first place the shock wave is forming, this kind of shock wave is forming. So that we are going to see in today's session. Okay, so before moving on to that one, so let me introduce you the idea of the speed of sound, right? So we all know how Mach number is defined. So Mach number is basically a ratio of inertia to elastic forces, or we can show that Mach number can be defined as local velocity to the local speed of sound, right? So that is how we can define the Mach number. So now we see, say like I have an object which is moving at velocity v. Okay, it's a point object we are treating here, which is moving at velocity v, which is less than the speed of sound in the medium through which a point object is moving. Say it can be a beeper, something like that. So which is emitting the sound waves, so that travel at a speed given by a. So if it is a medium is gas, so then we can show that it is nothing but gamma RT. So this we have seen in our speed of sound session, right? So now you see at any given time t, so in which how much distance the sound is traveled. So that is nothing but this region of influence circle. So it is emitting sound in all the direction, right? So it is moving in all the direction. So in a given time t, how far the disturbance is traveled or the sound is propagated. So that is given by this region of influence circle. So with the radius at. So the distance is nothing but a into time. So we can easily calculate speed is nothing but distance traveled divided by time taken. So the distance is nothing but a into t. Similarly, in the same time t, if the object is moving with velocity v, how far the object is moved in given time t. So let us call it as y. So y is equal to v into t. So this much distance the object is traveled. So now you see here, since object velocity is less than the speed of sound, that means this distance y, that is given by v into t, the same time we are taking. So this value is less than this value, right? A into t. So x is equal to a into t, or I can say x is greater than y. So that is why. So your object is always going to be inside the region of influence, this circle, right? So this is the case when the object is moving slower than speed of sound. Let us look at the another scenario, say the same object, now which is moving at a speed which is greater than the speed of propagation of sound. So now in this scenario, what happens? Now you see, in a given time, still this region of influence is same, but in the same time, my object has moved out of the region of influence. So that means the sound wave is not reached this location. That means the information regarding the object is not reached this region in time t, but object has already passed it. So this is the scenario when the object is moving at a supersonic speed. So now you see, so it is emitting at time t1. So it is emitting a sound wave at time t1. At time t2, it is emitting at some other location, say like this. So this is the region of influence of the sound wave propagated when it is emitted at time t2, similarly at different time. So in the meanwhile, object has traveled this much time since it emitted its first sound wave, right? So this much distance it has traveled. So say it is y now. So x is still the same, x, right? So now if I join this distance to the speed of sound distance such that I am joining through a tangent which is connecting all this region of influence circles. So this angle, what it makes with the tangent to the direction of the object's movement is called a Mach angle. So you can simply show that if I make the triangle from this one, so we know the radius and the tangent will always meet at 90 degrees. So this is a Pythagorean triangle. So if it is 90, this is also 90. So this is going to be my hypotenuse. And so if I use the information that I have is this distance is a into t and this distance is v into t. So if I use that one, so that is going to be opposite by hypotenuse. So I can define in terms of sine of angle mu equal to opposite a into t divided by v into t. So since it is traveling at the same time, so I can cancel out time from both the sides. So what I get now is sine mu equal to a by v, or it is 1 over v by a. That is nothing but Mach number, right? So I can show that it is nothing but 1 by m. So this is the relation between Mach angle and the Mach number. So for any given Mach number, I can calculate the Mach angle, right? So this is how the object which is moving at a speed greater than speed of sound could emit this Mach wave. So the Mach wave is having this angle mu with respect to the object moving direction. Now, if I have a free stream or the say like I have a stagnant atmosphere over here through which object is moving. If I transform it to a relative frame of reference, say like object is fixed and flow is coming in this direction. So now what happens? As soon as it passes through a Mach wave, so it orients in this direction, right? So across the Mach wave, nothing changes. The properties remain same. It's fairly like a very weak shock wave through which isentropic process is still valid. So that's our assumption. But see, I have an object which has a sharp corner like this, right? So given by half angle theta, right? So sharp corners like this, which through which the if theta is not equal to Mach angle, that means I have a theta which is greater than Mach angle, then flow still has to pass and which has to move. So then in those scenarios, instead of this Mach wave, we will see a wave called oblique shock wave, which has angle beta, which is always going to be greater than Mach angle mu, provided theta is greater than mu. So now you see in this scenario, across the shock wave, the shock strength what we are going to see for an oblique shock wave, which is relatively stronger compared to the Mach wave. So across the shock wave, now I am not going to see an isentropic condition. So now I am going to see a condition such that the properties will change dramatically. Like normal shock wave, what we have seen, the properties will change dramatically. Similarly, across an oblique shock wave also, we can see the properties will change drastically. So what do we mean by properties? That means like if I have a given free stream conditions like pressure, density, temperature and all. So behind the shock wave, I can still see P2, pressure, density and temperature, they are going to change. So there is a jump in property. It is kind of a weak discontinuity in the flow field. So across which the properties will change drastically, right? So this is the idea behind how oblique shock waves are formed. So now we are going to analyze. So if I give you the geometry such that like the angle theta of the geometry and the upstream flow condition Mach number, can you judge or can you calculate the property change across the shock wave? What this body will experience, what pressure this body will experience, or what kind of temperature which is going to experience, can you calculate it? So that is the question we are going to address now. So we will come back to our usual idea of control volume analysis, right? So I have a oblique shock wave with an wave angle beta with respect to the, so measured with respect to the flow direction. This is my free stream direction. So now if I have this kind of a system, can I calculate the downstream property? Now you can see here. So I'm actually doing the component wise analysis over here, or you can see I have a normal component to the shock wave and the tangential component to the shock wave. So why we are doing in this way, that we are going to see, because oblique shock wave, unlike normal shock wave, which oblique shock waves are at an angle. So now I am kind of analyzing it in two-dimensional space instead of 1D flow, what we have seen in the normal shock wave. So that is why I'm splitting into a different components associated with the free stream. So then I am going to analyze it, and we are going to see that a very beautiful result, that the properties across the shock wave, oblique shock wave, which actually depends only on the normal component of the velocity. not the tangential component of the velocity. So that's actually we are going to see, that's the part of the result we are going to get at the end of the discussion. See now, I am drawing a control volume considering two streams. Between that, I am having a control volume drawn like this. So this is spanning in two dimensions, so it can span to infinity, or we can restrict to a width b, whatever. Okay, so now what I am going to analyze now is, so this is my velocity v1, and I am splitting this into two different components, say normal component u1, that is normal to the control surface through which a flow is entering, and tangential component. So this is, I am calling it as u1, this is, I am calling it as w1 or wt1, whatever. Okay, so these are the two different components of velocity. So there is a slight misprint over it, is w1. Okay, so this is w1, this is u1, so they are normal and tangential components of velocity. Similarly, I can also define mt1, that is going to be tangential component of Mach number, and mn1, that is normal component of Mach number. But all we are interested in is, like, when I analyze it, you see, we are interested in the flux term. So what do we mean by the flux term? That is nothing but the velocity vector times the area normal vector, right? So v dot ds. So whenever I analyze the flux term, you see the tangential component is going to have zero flux, because the dot product of this vector and the area normal vector is going to be zero, because they are at 90 degrees to each other, because area normal vector will be pointing something like this. Say this is my area normal vector n. So n and tangential components will be 90 degrees to each other. So the cosine of 90 is going to be 0. So flux in a tangential direction is going to be 0. Whereas for the area normal vector with the normal component of velocity, so we will still have a flux term, so which is going to be maximum, because either I will be having v dot ds, that is going to be u1 times area 1, say like this is my area 1, depending on whether these two vectors are at an angle 180 degree or 0 degree. So this flux term will get the negative sign or the positive sign. That we were going to see when we apply the governing equation, right? So the system is clear now. So here A, B, C, D, E, all these represents the phases. Because it's a 2D system, we are not seeing the third direction. That's why I drawn a small box over here. So this is my B phase, this is my A phase, this is again, if I have this other phase from the bottom, so that is going to be my F phase. Similarly, I can draw the similar control wall surface over here. So that is going to be E phase, D phase, and C phase. They are the phases. Okay. So as soon as the flow passes through a shock wave which turns by an angle theta, so that is a deflection angle theta, right? Okay, now we will try to apply the governing equation to the system. Okay, so if I apply the continuity equation, so it's an integral form of a continuity equation. So again we will see here rho times v dot ds is equal to 0. So this is the flux term, and we discussed already the tangential component is not going to contribute anything towards the flux, because v dot ds is 0. So only component which is going to contribute towards the continuity is the normal component of velocity. So that is u times a1. This is negative because the incoming flow vector or u1 is in this direction, whereas area normal is in this direction at the inlet, right? So whereas at the outlet we have the system like this. So area normal vector n and velocity vector, both of them are in the same direction. So this is going to be positive, right? So now, since we are considering the streamlines such that this width, whatever we are having over here from here to here, it is same from here to here. So the area of face A and area of face B is going to be same. So I can easily cancel out A1 and A2 from both the sides. So now it becomes rho1 u1 is equal to rho2 u2. Note here, this velocity component is normal to the flow direction, or normal to the oblique shock wave, not the flow direction, normal to the oblique shock wave. Right. So this is my continuity equation. So now if I go on to apply the momentum equation, there is a catch. Momentum equation is not a scalar equation. It's a vectorial, right? So now I have to split that into two components of velocity that is relevant for this particular system which we are analyzing. So here I have a tangential component of velocity and the normal component of velocity. So the tangential component of velocity, if I use that one, my momentum equation in tangential direction is going to be rho v dot ds times w, that is a tangential velocity, and p ds in tangential direction. Now interesting here, we are going to consider this part is 0. If you look at the next step over here, you can still see like anyhow v dot ds in tangential direction is going to be 0. Note here, this v dot ds encloses the contour S. It is not just the tangential surface, it's the contour which is we are actually interested in. So here still we have two parts, so that is tangential plus normal, but we already know that the tangential component of this flux term is going to be 0 because v dot ds is 0. But still we have the normal component of flux term which appears in our equation. But the interesting point over here is PDS tangential component, so which we are keeping it as 0. Why? So that's again the question, right? Again we will go back and see this part very carefully. You see, when I do the contour integral, you see there is the surface which comes in this, right, face B. Similarly, there is a face F. So they are actually parallel to each other, and the pressure what you experience in this surface, right, and this surface is not going to change. So we are still in the same medium, and the pressure is not going to vary in this direction at all. So that is why these two parts, and they are opposite to each other and parallel to each other. So the pressure part in tangential direction is going to cancel each other. So that is why we don't see this tangential component of pressure term in the next step. So we are making it 0 since they are parallel surfaces, we don't see them. And other argument is like in the phase A and B, there is no tangential pressure. There is pressure is always acting normal to the surface, right? So I have a phase A like this, and this is my phase B, and we consider our phase F and all. So on this surface, the tangential component and pressure is always acting in this direction. So there is no logic if I say the tangential pressure on this one. So there is no tangential pressure. Pressure acts normal to the surface. So that is why that part we don't see a pressure in the surface A, but whereas in the surface B and surface F, the pressure is acting this one, and area is already in the tangential direction, but it is going to be 0 because which cancels each other from upper side and the lower side. So that is why we are keeping it as 0. Okay. And since area 1 and area 2 are same from our analysis, these are the normal areas at phase A and phase D respectively. So this can be easily cancelled out. So then I have rho1 u1 w1, rho2 u2 w2. And I know from my continuity equation rho1 u1 should be equal to rho2 u2 that we already obtained. So if I use that continuity information, so I can write on this step further rho1 u1 w1 plus rho2 u2 w2 which is equal to 0. So now I can take out these terms rho1 u1 equal to rho2 u2. So I can cancel these two and I am left with minus w1 plus w2 equal to 0, or I get a very beautiful result that w1 is equal to w2. This states that tangential component of the flow velocity is constant across an oblique shock wave. Very important result. So see, this is not an assumption through which we started. This is the result we obtained by doing the momentum balance in the tangential direction. So this is not an assumption. So many a times people will start like in oblique shock wave, we assume that tangential velocity components are same. No, it is not an assumption we started with. It is a result or an artifact of a momentum equation. When we do the systematic analysis, we obtain it as a result. So it is very important result, right? Okay, so let us move on to the another component of a momentum equation, that is the normal component. So similarly, so momentum equation in normal component is written over here in an integral form. So this is my u component and this is the pressure in the normal component. Okay, so now we are analyzing in a normal phase. So the phases other than like A and D, all of them are having a tangential direction. The area is tangential to the flow direction. So it makes no sense to use those areas to the normal component of pressure calculation. So they are omitted. But the normal component I have at the phase A, that is P1 A1, but P1 is acting in this direction and A1 is acting in the opposite direction. So that is why I have a minus P1 A1. Similarly, P2 A2 is the same direction through which the pressure and the area are directed. So now it is P2 A2 and this negative sign is already there in the momentum equation. So I have this negative sign. So this comes out to be P1 A1 minus P2 A2. Fine. So left hand side, same thing. V dot ds in tangential direction is going to be 0. But whereas in the normal direction, we have that component exists, the flux exists. So I am left with rho1 u1 a1 times u1 plus rho2 u2 a2 times u2 equal to p1 a1 minus p2 a2. So or I can take all like terms or like the at the upstream part one side and the downstream part other side. So I get like p1 plus rho1 u1 square is equal to p2 plus rho2 u2 square. Note here, since a1 is equal to a2, so I can cancel out a from equation. So I am just left with p1 plus rho1 u1 square is equal to p2 plus rho2 u2 square. So this is my momentum equation. Again, you see here, I have only a normal component of velocity which is appearing in my governing momentum equation, right? So this is again a very important result. So now similarly we can see the energy equation. Again the argument is same. The v dot ds in tangential direction I can take out. So this is going to be 0. Similarly on the right hand side also tangential part is going to be 0. Only normal component of v dot ds appears in the moment energy equation as well. And note here, this is not a vector. This is a velocity squared. That means it's a magnitude of velocity which is squared, right? So it's a scalar. E plus v square by 2 is a scalar and this is a actual velocity. It is not component. So that is why you see here still I am using only v, not like u. This is a vector. So this one I can split into u and w, but this is a magnitude. So I am not splitting. So it is not vector. It's already a scalar. It's a kinetic energy, right? So I have E1 plus V1 square by 2 times U1 A1 plus like same thing U2 A2 in the right hand side, I have only normal component which exists. The v dot ds in the tangential going to be 0. So I left with p1 u1 a1 minus p2 u2 a2. So now I am taking all the terms to one side and taking out area from the equation, because a1 is equal to a2. I can cancel throughout the equation. So I am left with rho 1 u1 times. So here also what I am doing, so here I have p1 u1. So I am multiplying and dividing by rho 1. So similar to this one, I am doing p2 u2 multiplying and dividing by rho 2. So what happened now? So I can easily take rho 1 u1 and rho 2 u2 outside from this entire equation, and I am left with e1 plus p1 by rho 1 plus v square by v1 square by 2. Similarly, rho 2 u2 times e2 plus p2 by rho 2 plus v2 square by 2. What is this? Surprisingly, we already seen this one during our discussion of stagnation properties. So this is nothing but enthalpy, right? So enthalpy is defined as H is equal to internal energy plus P by rho or E plus P into specific volume. So something like that. So this is nothing but enthalpy, specific enthalpy. This is a specific kinetic energy, right? And if I use the continuity equation, the result from continuity equation, that is rho 1 u1 is equal to rho 2 u2, I can cancel these. So what I actually left with, h1 plus v1 square by 2 is equal to h2 plus v2 square by 2. What does it indicate? So we should get this idea as soon as we see in this form. So this again states that the total enthalpy across the oblique shock wave remains constant. So this is the familiar results we already seen, right? So this is nothing but H01, which is equal to H02. So total enthalpy across the oblique shock is again constant. So that is very interesting result. And again, we can go on to show that v square is nothing but u square plus w square. It's the magnitude of the velocity, right? So if I use that idea over here, so v1 square minus v2 square, which is equal to u1 square plus w1 square minus u2 square plus w2 square. So that means we already obtained a result that tangential component of velocity across normal oblique shock wave remains same. So w2 is equal to w1. So if I use that idea, so this and this get cancelled. So I am left with u1 square minus u2 square. So that is nothing but I can replace v1 square minus v2 square with u1 square minus u2 square. So this equation again can be shown in this way. Again, you see here, even the energy change across the oblique shock wave depends only on the normal component of the velocity, right? So this is very important result. So now what we are going to do is, since we obtained our governing equations for the oblique shock system and we obtained or arrived at a conclusion that the property change across the shock wave depends only on the normal component of velocity, so it is easier for us to analyze the oblique shock property changes using the normal component of the Mach number instead of using only like actual flow Mach number. What we are going to do is, like, we are going to transform our system into normal shock wave system. So that means I have an oblique shock wave. I have a free stream velocity corresponding to free stream Mach number m1. So what I am going to do now is, just use the different color. So what I am going to do now is, like, I am going to do the tangential component and the normal component. So, right. So this is my mn1. So that is normal component of the Mach number, and mt1. So that is the tangential component of the Mach number. Similarly, if I, in the downstream part, I can split like this, 90 degrees. This is m2, actual Mach number, downstream of the flow. This is mn2. This is MT2. Note here only WT1 is equal to WT2. It doesn't necessarily mean that tangential component of Mach number is also same. So no, that we are going to see later, but it doesn't necessarily guarantee you that to state tangential component of Mach number across the shock wave is going to be same. No, it is not the conclusion we are going to take from that result. So only result so far we got in terms of tangential component is tangential component of velocity across the normal shock wave does not affect it. So or it is not affected and it is going to remain same. That's what we concluded from our momentum balance, right? Okay. So now, so this is a shock wave at an angle beta, and this is the flow turn angle theta or the deflection angle theta. So now you see this is parallel to the oblique shock wave. That means what is this angle? This angle is going to be beta only. And what is this angle? Angle between this velocity vector v2 or the m2 component to the oblique shock wave. What is this angle? So this is beta minus theta, right? So this angle is beta minus theta, right? So now if I want to calculate the normal component of velocity from here, right? Yes. So now I have the system with normal component of velocity, which can be shown as mn1, which is equal to m1 times, see, this is opposite side. So this is hypotenuse. So sine beta. Similarly, I can define mn2 equal to m2 sine beta minus theta, right? So I can calculate the normal component of velocity. So when we are analyzing this system, so given the upstream Mach number and the deflection angle theta, so what we are going to do is, so we have to find out the theta, beta and Mach number relation. So we will get the plot for the corresponding relations. So that we are going to see a bit later. But what usually we do is, so given m1, we will get the beta and then we will calculate the Mach number mn1. So then we use the normal shock wave relation. So that means like, so given that if I have mn1, which is calculated using m1 sine beta 1 or sine beta, not beta 1, m1 sine beta. So then I am going to calculate, if I want to calculate the downstream Mach number, so I am going to calculate mn2 first using function of mn1 using normal shock relation, which we have already seen. And we again use the mn1 as a reference to calculate P2 by P1. So that we have seen, right? 1 plus 2 gamma divided by gamma plus 1 times. We had m1 square for normal shock wave. Instead of that one, I am going to use mn1 square minus 1, right? So what is mn square? So that is nothing but m1 sine beta. So m1 square sine beta square minus 1. So this we are going to use. So similarly, rho 2 by rho 1, we will write it as function of mn1. Similarly, t2 by t1, function of mn1. So we will calculate the property change across the oblique shock wave using normal component of velocity. So normal component of Mach number, right? And we use the normal shock wave properties first by calculating normal component of Mach number. We are not using this one directly, right? That is that you have to keep in mind while doing the calculation. Fine. So what we have analyzed so far is like how the properties change across the oblique shock wave depends on the flow geometry. And if I ask you a simple question, can a oblique shock system be uniquely defined with a single parameter? So if that is the question, then you have to ask very carefully, because oblique shock wave is kind of a two-dimensional system. So by giving only one property, I cannot define the property change across the oblique shock wave. Either I have to have at least two properties, say like m1 and theta, or m1 and beta, or m1 and p2 by p1 kind of thing, shock strength, or something like that. Like I need at least two properties to define the oblique shock system uniquely. So that is why very important thing in oblique shock calculation is like, you should know how to analyze the system for a given problem, right? So you should see whether the given information is sufficient or not. If it is sufficient, how you can approach for it. So that is the thing you have to very carefully, you have to analyze it very carefully, right? So that concludes our part 1 of this oblique shock relations. In the next session, we are going to see the theta beta Mach relation and how they are related, and again few problems from the previous year gate on oblique shock wave. Okay, so thank you for attending this session. See you.